This is the limit definition of the derivative. At the moment, it's the only way we know how to compute derivatives. That might change in the future if you're good. But for now, if there's a problem that says compute the derivative, you'll be using this limit. Of course, we have another way to represent a derivative, Leibniz notation. If y equals f of x, then the derivative is dy dx. This notation might seem more confusing, but it's actually far more useful, especially for multivariable calculus. For now, think of it as your function is on top and the variable is on bottom. What comes after first derivatives? Second derivatives. These are just the derivative of the derivative. The notation is f double prime of x, or f2 of x, which is nicer for fourth or fifth derivatives, or in Leibniz notation, d2y dx squared. This says the second derivative of y with respect to x twice. Not all functions are differentiable. Remember, a derivative is a limit. That limit must exist for the derivative to exist. Think about a discontinuity. When we get closer to the jump, the tangent line gets more vertical, which is bad. This is not differentiable. What if there's a sharp corner? From each side, the tangent line is different, so again, not differentiable. A nice smooth curve? Now that's differentiable. A nice analogy is water. Water always travels in a differentiable path. As long as the hose doesn't have too sharp of a bend, water comes out the end. If there's a sudden kink in the line, the water stops. The path is no longer differentiable. The water only continues once the differentiability is restored.